become the building block of civilization. The main component of everything from roads and runways to buildings and bridges. Now, concrete on Modern Marvels. $110,000 tons of concrete were used to build the Seattle Kingdome in 1976. Its enormous concrete roof spanned almost 8 acres and weighed 25,000 tons. Designed as a multi-purpose stadium, it acted as a concrete umbrella, protecting its occupants from the Pacific Northwest's notoriously fickle weather. The Kingdome became an exclamation point for downtown Seattle. And because of the concrete structure's durability, it was expected to stand the test of time.
8, 7, 6, 5.
But it was not to be. It took just seconds for dynamite to demolish what had taken years to design and build. On a Sunday morning in March 2000, the Kingdome's concrete was blown to bits in a rapid-fire series of detonations. 53,000 cubic yards of concrete imploded in the blink of an eye.
When you watch the Kingdome in Seattle as it's imploding, being demolished in a big explosion, you have to say, why? Why has it only been 30 years that we've used this building? Well, it happens that it outgrew, the needs outgrew the structure.
Over the years, the Kingdome's concrete had undergone some extensive renovations, but its strength and durability were never questioned. When Seattle's football team was sold in the late 1990s, its new owner was guaranteed a new stadium. That sealed the Kingdome's fate.
It doesn't mean that the concrete materials have gone bad. It's no different than many of the other buildings that have been taken down in order to make way for new structures as we have new needs in the community. This has been happening throughout the ages.
And throughout the ages, it is the development and use of concrete that has made it all possible.
Well, concrete is a composite material. It's an artificial stone, and it is made of sand, stone, water, and cement.
Each of its ingredients is essential, but it is the chemical composition of cement that makes concrete possible.
There's a saying in the concrete industry that cement is to concrete as flour is to cake.
If concrete begins with cement, then cement begins at the rock quarry. Huge rocks and boulders are crushed into a rough gravel. At a cement plant, they're ground into a fine powder which is mostly limestone. It's then mixed with small amounts of calcium, silicon, aluminum, and iron. This material, known as raw meal, is now ready for the kiln, a huge cylindrical furnace. A modern kiln is 100 yards long, the length of a football field. It's the world's largest moving piece of equipment and one of the hottest. The raw meal enters the kiln's upper end. As it turns, the material moves through progressively hotter zones. As it tumbles down the rotating kiln, it is heated to a temperature of 2,700 degrees Fahrenheit and becomes partially molten. Under this intense heat, individual molecules break apart and recombine to form a new marble-sized component called clinker. Once it is cooled, the clinker is mixed with a small amount of gypsum, then ground into the superfine powder known as Portland cement. It got its name because it resembled stone from the island of Portland, England.
Portland cement is the thing that binds everything together.
To create concrete, the cement is blended together with water, forming a paste that coats the surface of the final ingredients. Sand and hard, coarse stones known as aggregate.
When water and cement mix, it begins a process called hydration, which is a chemical process, changing its properties. It goes from a very plastic liquid state to a hardened state. And that process is what combines all of the sand and the gravel and the cement together into this hard mass.
Concrete has evolved into a critical component of modern civilization.
You see concrete every day. You walk on concrete sidewalks, you drive down concrete roads, you go to work in a concrete building, and some people go home to live in a concrete house.
Concrete is the building block of civilization.
Concrete is as ancient as it is modern. The history of cementing materials together goes back to the time when prehistoric man abandoned his caves to build shelters. He used mud and clay to fill in the gaps between stones, to keep out the wind and the cold. Later, the Assyrians and Babylonians used clay mixed with straw. The straw gave the earthen material packed around it a rough skeletal framework and allowed it to be shaped. The Egyptians used lime and gypsum, a mineral rich in calcium sulfate, to create a material that would harden even better.
The Egyptians may have been using lime and crushed stone to cast certain shapes, small shapes, and use them on their buildings and monuments, but they had not discovered concrete as we know it today, which is a much stronger material.
The Greeks made further improvements. Then the Romans perfected a cement that produced structures of remarkable durability.
We have to go back to the Roman Empire and the ingenuity of the Romans. And the aqueducts, to me, are probably the best and the greatest thing they did.
It was only in the ash of the volcanoes that developed the Roman concrete.
That volcanic ash would come to be known as pozzolan.
It is a very fine dust, which is good for the concrete because you got a lot of surface area to it. And so when they took the pozzolan and mixed it up like they would put it on the wall, holy moly, all of a sudden they get a real material that'll set hard underwater.
Pozzolan was the key ingredient in what would become known as Roman concrete. It was essential in building the Pantheon.
The Pantheon is a building that is a round building. It's 100 feet high. It has a dome of 143 feet in diameter. Now that's a big building for any engineer to look at.
How did they accomplish this? This was a huge open space with a single domed closing on the top. And yet, that was 2,000 years ago. Well, the Roman engineering really developed quite a bit in the highway, in the water transportation, and in the materials area. They learned very specifically how to handle concrete.
While the best examples of Roman architecture still exist today, whatever knowledge their architects had disappeared when their empire faded into the pages of history.
The quality control features of making concrete was forgotten. It's as simple as it was. They lost the recipe how to control the quality of their product.
During the Middle Ages, European architects concentrated mainly on building castles and cathedrals of huge stone instead of concrete. It wasn't until almost 1,800 years after the fall of the Roman Empire that an experiment by English chemist John Smeaton led to a true discovery. In 1756, Smeaton was given the job of rebuilding the perpetually crumbling Eddystone Lighthouse.
He used some of the real clay limestone sources that he cooked or burnt to make a material. It was called hydraulic lime. And he used this for his blocks mortar he needed in the lighthouse. It wasn't a very outstanding material, but it worked underwater. I think it was a definitive moment.
Mortar is the plaster that holds stones together. In order to create a material that binds properly, Many scientists experimented with grinding limestone and clay together. But it wasn't until 1824 when another Englishman, Joseph Aspdin, made a major discovery. He burned his mixture of limestone and clay into lumps and then crushed the lumps into a fine powder. When he mixed it with water and sand, it made a strong mortar that would harden underwater. Aspdin obtained a patent for his product in 1824. He called it Portland cement.
His claim to fame is that he patented the process that these other people had been doing for the last 50 years.
Portland cement would come to define the concrete industry. But the next 50 years would lead to a series of new developments that would change the use of concrete and the world forever. At the beginning of the 19th century, the United States was still in its relative infancy as an independent nation. But with its ties to England broken, America had begun a period of rapid expansion that had to rely on its own natural resources: coal, minerals, timber, and water.
The Erie Canal seemed to me to be a real starting point.
Construction of the Erie Canal began in the state of New York in 1817. It was designed to be a vast transportation system, stretching 360 miles long. The waterway would have more than 80 changes in elevation, called lifts.
Well, these lifts required structures, and the structures required hydraulic, lime to put them together. So there was a demand, and it just so happens that they found a natural cement that could be heated.
Erie Canal engineer Canvas White experimented with different kinds of rocks in the area, heating and then crushing them into a coarse powder, which he then mixed with water. Builders would soon begin batching their own versions of White's crude formula on a variety of structures. They used stones of any kind, sometimes even crushed oyster shells, to create a paste that could hold a wall together when it hardened.
In the past 200 years, there's been a very rapid growth, starting in the 1840s, with steel, with glass, with aluminum, with ceramics, with rubbers, and concrete. I think, in fact, that our world civilization reached a point that we needed these materials.
By the 1850s, Portland cement had become widely used in Europe, and it was there that a major breakthrough was made that would forever change concrete construction. The first use of iron to strengthen concrete by reinforcing it internally.
Reinforced concrete is concrete in combination with some other reinforcing material, usually steel, that when used with concrete actually works to resist both compression and tension in the concrete.
Tension is a pulling force that acts in one direction. An example is the force of a cable that is holding a weight. Under tension, a material usually stretches and returns to its original form if the force doesn't exceed the material's limit. Greater forces create greater tension, which can rupture the material. Compression is the decrease in a material's volume that results from the application of pressure. That pressure can come from one or several sources.
Tensile strength is the ability for a material to resist pulling or tension. Pulling is simply pulling material so that you're trying to pull it apart, as opposed to compression, where you're trying to push it together. Concrete, historically, and just by nature, is stronger in compression than it is in tension.
The invention of reinforced concrete is usually attributed to a Frenchman, Joseph Monnier, who made garden pots and tubs with concrete reinforced by iron mesh. Monnier patented his discovery in 1867.
Pretty soon, others in the building trade saw it and began to think of how they could use the material elsewhere. If you could make a pot that strong and that thin and that light, imagine what we could do in the walls of a house or the roof of a cathedral.
The first reinforced concrete structure in the United States was a mansion in New York that made extensive use of concrete beams reinforced by iron joists.
When designers begin to understand how to design reinforced concrete members, the use of concrete for structures actually expanded significantly. Now they could design more slender beams and columns using reinforcement that they couldn't ever do before.
Industrial expansion called for a stronger and more uniform material than natural cement. By the 1870s, American engineers had begun to specify the use of European Portland cement for their projects. A Pennsylvania man was convinced he could produce Portland cement in the United States that was just as good as the German and English cement being imported. In 1874, David Saylor founded the Copley Cement Company in the Lehigh Valley area of Pennsylvania. It would come to be known as the birthplace of the U.S. cement industry. 60-foot-tall brick kilns were built to handle the increasing demand. Soon, stationary kilns would be replaced by rotary ones.
It really changed. It mechanized the concrete processes. It could continue day and night making concrete.
That's way you could continually, from the mine, you could keep dumping rocks into this kiln forever. And it would continuously create, you didn't have to cook the thing for 24 hours, empty it out, and then restart a new batch. You're essentially batching the stuff continuously.
It was around this time that Thomas Edison took an active interest in concrete. In 1902, the famous American inventor founded the Edison Portland Cement Works in New Jersey.
Edison also had this great idea that he could preform a house. He could make a prefabricated house out of concrete. He thought he could make up a set of very complicated forms that were expensive at the time, and that he could cast a house and then just take all the form work off, go to the next place and make another house.
Edison completed several homes and boasted that they would last for centuries. The process didn't catch on though, but once again, Edison had the right idea.
History has proven Thomas Edison right. Concrete is a very durable material, it's a very economical material, it's a very strong material, and we still can go back and look at Thomas Edison's houses today.
Within a few years, reinforced concrete had become an economical substitute for stone, since it was cheaper to produce than stone was to quarry. Designers and builders began work on structures that utilized concrete's new architectural companion, steel. When the Ingalls Building went up in Cincinnati, Ohio in 1902, it became the world's first skyscraper.
It was a 16-story, 210-foot building, and it was twice as tall as any concrete building had been before it. There's a story about a newspaper reporter who waited across the street from the building all night because he was convinced that it was going to collapse of its own weight. So people really were in complete disbelief. They really didn't believe that this building would stand, and it did. It shocked everyone.
When the Ingalls Building was first designed and built, we had very limited understanding, engineering-wise, as to the behavior of the material and the behavior of the composite material of the reinforcing steel working in conjunction with the concrete.
In engineering, the term tensile strength refers to an object's resistance to forces that threaten to break it apart. Concrete, though strong in substance, is weak in tensile strength.
So if I had a beam and I put a load on the top of the beam, if it did not have reinforcing, the beam would crack very easily and, of course, collapse. However, if we put a steel bar inside the concrete and we take this beam and we put load on top of it, the reinforcing bar becomes in tension and can support a much greater load than an unreinforced concrete beam.
While America's skylines were changing, so were its roads. Up until now, roads were made of dirt, gravel, stone, or brick. The first concrete road in the United States was built in Bellefontaine, Ohio, by George Bartholomew in 1894.
The American public definitely needed to be sold on the use of concrete as a paving material.
At first, only a small section of Bellefontaine's Main Street was paved with concrete. City officials were skeptical. They thought it would crumble and crack. they required a guarantee that the pavement would last at least 5 years. It did, and then some. While horses and wagons soon gave way to motorized vehicles, the American cement industry was changing too. What began as an informal business association in Chicago, Illinois, evolved into an organization that would dominate the business.
The Portland Cement Association was started in 1916, and it started at the same time that the first Federal Aid Highway Act was instituted. So the first thing the PCA did was they launched a massive national advertising program to promote the use of concrete and paving. There was a huge sales pitch. They paved 1-mile stretches of concrete pavement in different parts of the country in an otherwise unpaved area, and we called them seedling miles. So farmers and other people in their automobiles would drive along an unpaved road and then hit a smooth expanse of concrete pavement, realize how amazingly better the concrete pavement was, and petition their local officials and demand concrete pavement.
The organization ran a series of ads in magazines and newspapers, selling the American public on the benefits of concrete.
And one of their biggest slogans was "Concrete for Permanence." One of the most famous ads that we ran was in the Saturday Evening Post, and it was touting the use of concrete roads that children could be off to school on any day. And they said, "Over the concrete road, so even that children can roller skate upon it, so strong that heavy trucks at high speed cannot break it, so enduring that years of motor traffic cause no appreciable wear, unaffected by moisture, heat, cold, or frost, and maintained at very low annual expense."
Soon, engineers were learning how to better produce this new building tool.
In the 1900s in the United States, concrete was made at the site. It was mixed in a small mixer right at the site, and the workmen put in all the components, and many times you got poor qualities of concrete at that time because there wasn't a lot of control.
That was about to change.
It started out in the early 1900s with horse-drawn trucks, mixer trucks.
As the horse or mule pulled the mixer, wood paddles would stir the mixture while water from a small tank was added. Because of its size and weight, these mixers were limited in the amount of concrete they could handle. By 1916, steam-powered rotary drum mixers were being used, and in the early 1920s, gasoline-powered paving mixers were being mounted on trucks and driven to job sites.
One of the most important events in the use of concrete is the development of trucks that actually deliver concrete to the site, whereas in the past you really had to mix the materials on site to use it.
As fast as Henry Ford was building cars, engineers were building roads and highways that connected cities and towns. Both concrete and asphalt were used.
Concrete roads cost more but lasted longer, and asphalt roads cost less, didn't last as long. So it was a question of economics.
While road builders were busy connecting the country, engineers were setting their sights on projects of a much larger scale. Dams. Ever since the beginning of civilization, man has attempted to control water. But to do that, you must control nature itself. Engineers around the world have accomplished that feat with concrete dams. It will take hundreds of millions of tons of concrete and 16 years to build the Three Gorges Dam in China. The gargantuan structure designed to eliminate flooding along the Yangtze River is China's biggest construction project since the Great Wall. Three Gorges will stretch 1.5 miles long, much wider but not nearly as tall as the granddaddy of dams in the United States, Hoover Dam.
I think Hoover Dam does become the benchmark for anybody talking about dams in the U.S.
It took more than 3 million cubic yards of concrete to create Hoover Dam. Built on the Colorado River near Las Vegas, Nevada, Hoover Dam weighs 6.5 million tons. It stands as tall as a 70-story building. It was poured in thousands of separate pieces, then linked together. literally forming a concrete curtain. Construction crews not only had to deal with soaring desert temperatures, they had to contend with the massive amounts of heat generated from the concrete as it cured.
All concrete, as soon as the cement, the binder, mixes with water, and it gives off heat. In a dam construction, however, it still becomes a very serious concern because of the temperature buildup within the structure.
On Hoover Dam, miles and miles of pipes were built into the dam and carried cold water through the dam while the concrete was curing. If the dam had not had those pipes for cooling, it would have taken 200 years for the temperature of the concrete to reach ambient conditions.
Vibrators were inserted into the freshly poured concrete, literally jiggling it and removing air pockets. Modern dam designers still vibrate freshly poured concrete, but more and more are turning to a newer and drier form of concrete.
Roller compacted concrete is still concrete, and it's a type of construction more than a change in material.
Roller compacted concrete is a very stiff mix of aggregates and sand and cement. It's only under the high pressure, the heavy load of the roller, that actually compacts it into something tight enough for you to actually use it. We dump it out of a dump truck and we run over with it with a steamroller, essentially. And we keep doing that in layers until we're 200 feet up in the air. Basically, as fast as you can make concrete is how fast you can make a dam.
If concrete dams are designed to hold back water, concrete bridges are built to traverse over it.
The challenges are the same for any bridge designer from the beginning of time. The loads it has to carry.
The first concrete bridge reinforced with steel in the United States was built in Rock Rapids, Iowa, about 1894. As concrete bridge making evolved, it embraced the principles of pre-stressing, using concrete structural members along with reinforced steel strands to increase its inherent lack of tensile strength. The cables are stretched tight, like a rubber band, inside sections of concrete as it is being poured. The hardened concrete now includes the extra strength of steel.
Pre-stressing is something that complements concrete. Concrete is a compressible material. It'll hold tremendous loads compressing it. But if you try to bend it, it'll crack. So what we do, we add pre-stressed strands, and these strands, if you can envision a block of concrete, you have a pre-stressed strand that goes all the way through the block. You pull on that strand, and it pushes the concrete together. And it takes the tension at the bottom of a span for the concrete. And then the top of the span becomes in compression. So now you have an element of concrete and steel that is extremely durable.
The first major bridge to use this technique was the Walnut Lane Memorial Bridge, built in 1950 in Philadelphia, Pennsylvania. Gene Figg continues the tradition of American concrete bridge making from his Florida office. Figg Engineering has designed some of the world's most sophisticated concrete bridges.
We feel that America deserves better and beautiful bridges. We also believe that the bridges we're doing are we're creating bridge art. And we feel like by utilizing concrete in many different ways, we're able to create an art form.
Figg's company designed the Natchez Trace Parkway Arch Bridge. It was built in 1996 near Nashville, Tennessee. It's America's first and longest precast segmental concrete arch bridge. In theory, building a segmental bridge is like stringing beads together on a necklace.
The Natchez Trace Arches was a chance to cross a valley, and at the same time, it was a chance to really utilize different shapes of concrete. And it all comes together with seamless appearance because it all matches, which is one of the key things in a bridge. If you can get a seamless connection, then the bridge, you don't know why it looks good, but it really looks good.
The Sunshine Skyway Bridge in Tampa, St. Petersburg, Florida, is among the company's many other signature concrete bridges. This is what is known as a cable-stayed bridge. It's created a thin silhouette of concrete that seems to float in midair.
If we're going over water, we try to have the bridge have some shape to it that's not just a straight bridge, it has some movement to it. The Sunshine Skyway Bridge is distinctive because it has an element of a sailboat going across the whole bed.
But when you build a concrete structure like this, you expose it to the elements, wind, rain, and salt water of any kind.
The environmental enemy of concrete would be salts. The cracks are the problem. Cracks in the concrete cause the seepage of this salt material to go down and corrode the steel. These concrete bridges can, today with the performance you can get from the concrete and the pre-stressing, you'll end up with a bridge that's really just so durable that the life is more than 100 years.
Concrete has become an indispensable building material of modern times. It is formed into giant slabs for airport runways, molded into miles of superhighways, shaped into precast sections of bridges, and poured into the foundations of eye-catching skyscrapers of enormous weight and girth.
The process of taking a fluid material, pouring it into a form, and having it set up to something that can support a 100-story building is amazing and is one of the prime properties of concrete.
Concrete's an exciting material. You know, people think of concrete as the gray stuff, the sidewalks we skin our knees on, that material we sneak our handprints into.
But concrete's pluses are also its minuses. By its very nature, concrete is an extremely heavy material and not flexible.
All concrete cracks, it's the nature of concrete to crack. Concrete buildings, of course, are subjected to a lot of different environmental conditions. Some of these environmental conditions are forces, such as earthquake forces or wind forces, tornadoes and hurricanes.
The taller the building, the greater the wind forces that push it back and forth. But the greatest and most unpredictable threat to a concrete structure comes from the ground up.
Earthquakes create a lot of forces in buildings from the ground shaking.
San Francisco, California was practically destroyed by a powerful earthquake in 1906. The entire Bay Area sustained major damage from another tremor, the Loma Prieta quake in 1989. In Southern California, the 1994 Northridge earthquake destroyed freeway overpasses and collapsed buildings. Even the mighty strength of reinforced concrete must yield when the Earth's tectonic plates collide.
Earthquakes are a real nasty thing. Here's the building sitting in the air, and here's the building, here's the ground. Well, the building doesn't know that it's supposed to move with the ground, so it's sitting, and there's a shear condition that moves across the picture and it cracks everything, cracks all the concrete and bends the steel and cracks the steel. So what you have to do is design these structures to take an estimated shear so that it won't bend. It moves, but it doesn't bend.
Scientists have been studying the effects of earthquakes for many years. Quakes are often simulated in laboratory stress tests.
One thing about earthquakes is that we still don't have a great understanding of how they work. And so certainly after every earthquake, we gain some knowledge that we can then incorporate into our new building codes and our new design techniques.
Kobe, Japan, 1995. The city is decimated by a powerful earthquake. Hundreds of thousands of buildings are destroyed. It was a brutal lesson.
We're learning. A lot of things that had problems, either in California or in Japan, were buildings or bridges that were designed before we knew these things that we know today.
Another natural enemy of concrete is wind. especially the violent forces of hurricanes and tornadoes.
This is Hurricane Carla in all its strength. After several days of waiting in the Gulf of Mexico, late today it moved inland.
Hurricane Carla ripped through the Texas Gulf Coast in 1961. Its 2-day-long rampage left a wide path of destruction in its wake. Winds of more than 100 miles an hour sent deadly projectiles flying through the air like missiles. Concrete structures were better able to withstand the storm than other traditional wood-framed buildings.
3, 2, 1.
Lab tests have shown that walls made of concrete can withstand wind forces greater than any hurricane. Scientists use wind tunnel testing to help them better understand nature's destructive forces.
Each design has its unique situations as far as forces are concerned, whether it's the force of a hurricane wind or whether it's an earthquake, which is a different force. It's a horizontal and vertical movement all at the same time.
Winter weather is another environmental enemy of concrete. The continual freeze-thaw cycles of the seasons can shatter the microstructure of the paste that holds concrete together. Damage to the Baha'i Temple in Wilmette, Illinois, is a good example of the effects of weathering.
The microscopic bonds between the cement and the sand and the aggregate stones gets broken over time by this tiny bit of freezing and thawing action, so that you begin to have kind of a melting, a weathering away of the surface. The freezing and thawing effect on concrete will only attack the surface. It works from the outer areas in, because it takes moisture going into the surface of the concrete to generate that freezing effect. The pressure generated as water expands into ice pushes a wave of water deeper into the concrete.
It has taken a major renovation project at the Baha'i Temple to repair the concrete and restore it to its original condition.
Concrete is such a new material that we have not had the history of how does it break down in the weather. How does it break down from loads that continually come across it, such as when a train crosses a bridge? That's what we're learning. That's where we're improving.
A commercial jetliner touches down at a busy airport. But there's a problem, and the plane can't stop by the end of the runway. This is one solution. It's called a soft ground arrestor system, and it uses cellular concrete to stop the plane.
So if an airplane is going down a hardened concrete pavement and it gets to the end and the brakes didn't work, it goes into the cellular concrete, which is essentially a structural foam, and gradually sinks into this, and it's essentially an artificial brake.
The cellular concrete is somewhat like styrofoam, created with millions of microscopic air bubbles that are intentionally added during a precasting process. It's designed to be firm, yet flexible, and collapse on impact, crushing predictably.
The landing gear is a very expensive item on a jumbo jet, and so if you don't have to snap the landing gear to stop the plane, then there's a really good reason to have it.
Every year, the concrete industry holds a massive convention to show off what's new in the business. It's called the World of Concrete.
The World of Concrete is a blast. The World of Concrete is so full of people with new ideas, fresh ideas. They're working together, they're coming up with new mixed designs, they're making new things possible we've never seen before.
It's a giant concrete candy store where the latest tools of the trade are on display. At center stage, a new generation of mixing trucks that help supply a steady stream of concrete at the construction site. These state-of-the-art mixers use heavy-duty pumping systems to push the concrete where it's needed.
You have to have a mixture that flows through the pipes from the pump at the base of the structure. And you want to make sure that the concrete doesn't set before it gets all the way up to the top.
There's much that's hot and new and exciting in concrete today. The things that strike my fancy the most with concrete is the creative use of color and finish.
Modern concrete home builders are taking advantage of techniques and ideas that were pioneered by legendary American architect Frank Lloyd Wright.
Frank Lloyd Wright had a gift of pushing the envelope.
He just used concrete in ways that other people hadn't used it before.
Wright was once referred to as a rebel in concrete. He believed that a building should develop out of and exist with its natural surroundings. Wright personally showcased that philosophy in the late 30s with his legendary design and construction of the so-called Falling Water concrete house in Pennsylvania.
Frank Lloyd Wright used concrete as art, really. He liked to expose concrete. He used molds to develop patterns on his structures.
But the futuristic Johnson Wax building might be Wright's greatest work. Built in Racine, Wisconsin in 1936, it used the weight-bearing capabilities of concrete to create a futuristic working environment in a corporate headquarters.
When you see the Johnson Wax building, you begin to understand how Frank Lloyd Wright really understood, beyond architecture, the strengths of concrete.
Wright's early use of concrete blocks has led the way for dramatic new uses of concrete in modern home building. These insulating concrete forms are gaining widespread acceptance.
I would say the use of concrete for home building is probably the single most revolutionary use of concrete. Polystyrene forms that are stacked in place with polystyrene on both sides. Once you form the shape of your structure or home, then you place concrete inside. So once the concrete hardens, you have a super strong home that's also very energy efficient because of the insulation. It's also very quiet because of the concrete.
We can add any kind of external finishing from siding, brick, stucco, so they look just like any other house on the block. They don't look like a big gray concrete square. They can look like any home you see in a typical American neighborhood.
Concrete's lasting legacy will be its widespread use. The same substance that makes it possible to build something as simple and benign as a driveway also makes it possible to construct a military missile silo. Concrete is an essential part of civic icons around the world, from the Gateway Arch in St. Louis to the Space Needle in Seattle and the Opera House in Sydney, Australia. When concrete was fashioned into the Berlin Wall, it separated an entire country. But when it was used in the English Channel Tunnel, it brought two nations together. And when it was poured into the gigantic foundation of the Petronas Towers in Kuala Lumpur, it anchored the tallest structure in the world. Again. Every day, a new concrete building makes a new statement somewhere. And for the future, the sky's the limit.
You could make concrete on the moon. There's no reason you couldn't make Portland cement on the moon, because the raw materials already exist there. People have looked at the moon rocks and realized that what they call lunar concrete is entirely possible. The composition of the moon, of a lunar rock, is not that different from that of Portland cement. All you have to do is figure out how to make water.
Perhaps with space stations, ultimately, we may be able to take materials into space, mix it and make concrete as we know it here on Earth, and use it for construction purposes.
Yeah, I think sky's the limit. There's no place that you can't go and see concrete, and that's going to be true for the next 100, 500 years.